Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 37, we will talk about multinomial logistic regression. The different concepts that we will cover will be on multinomial logistic regression in general. Then we will talk about the model formulation, and then again we will show you how to estimate the beta coefficient using the maximum likelihood estimation. Then we will introduce the residential location choice model, and then we will use Python to determine the coefficients of a multinomial logistic regression, in this case the residential location choice model. So, multinomial logistic regression, or MNL in short form, is an extension of the binary logistic regression, and it is applied when the dependent variable has more than two unordered categories. That means instead of a binary outcome, we can have multiple outcomes. So, it models the probability of choosing one alternative among multiple discrete options relative to a reference or a base category. So, that means it always tells us the probability of choosing one option compared to the others. So, that is how it gives us. So, that means if I have got four modes, car, bus, metro, walk, and then we can say that what is the probability of choosing car in reference to walk, or what is the probability of choosing bus in reference to walk. That means compared to walk, will the probability increase or decrease, right? So, always one is taken as the base class, and then the others are reference class, and then the others are predicted as per that. Similarly, we can predict residential location choice. That means for a household which is trying to find an apartment or a location where to build a house or buy a house, we can use this sort of a MNL model to determine, based on the features available or the observations, we can say that, well, for a new household with the characteristics known, of course, which are the likely location this particular household will choose, right? So, this kind of models actually help us in predicting the location choices. It could be destination choice for a trip model. It could be, that means, a trip where he's ending up, where he's going, or it could be a location choice for a residential location choice model, or it could be a plain mode choice model as well. So, parking choice will somebody park on street, off street, illegally will park, or park and ride. So, this could be the choices. If categories are ordered, then in that case, suppose there is an order, like there is low, medium, high. So, that means the outcomes are also ordered. In that case, we will not use multinomial logistic regression. We will use a ordered logit or a probit model, which is a different model altogether. So, some of the assumptions of MNL are: observations are independent, log odds are linear in predictors, same as the binary logistic model, no perfect multicollinearity among predictors, and then there is a IIA assumption which says that the odds of choosing between two alternatives are independent of other alternative, or in other terms, we can say that if there are, in this particular case, the ratio of choosing car versus bus should not change if metro is introduced or we change something in metro. That is the odds of choosing between two alternatives, the relative probability between the choice between two alternatives doesn't change if we change some third mode. But actually, it's not always the case. But yeah, so this is something which is an assumption of the MNL model. So, the other thing is there has to be a lot of samples, again more than 300 to 350 that is recommended, and there is no complete separation in data, that is no predictor perfectly predicts a class. So, these are the different things that these assumptions has to hold true for running a MNL model. So, we use MNL when we have got n observations and each has got feature vectors of xi, that is xi could be xi, x12, xi1, xi2, xik and so on, and a category for every with a feature vector xi means for this feature vector could be many, and then there could be also multiple individuals, that is n observations. So for n observations we are getting this feature vectors which will that will also vary as well. And then there is a categorical outcome which is yi, which could be either 0, 1, 2 till j. So one of the categories chosen as the reference of the base class, usually class the 0th class. It depends. Sometimes the choice of this 0th class also depends on the nature of those variables as well sometimes. So here also we form a utility or a score function, same as the linear regression, as the binary logistic regression model. So the linear score is computed for each non-base class j, and as you can see, this is the equation, and I is equal to 1 to n, where for it could be one individual, one household, one trip, one record. So whatever is the unit of analysis for that, this is for each individual, these choices would vary. So that means for each base class, that is j base class, we have to determine the score for each one of those, right? And then these values would also vary as per each individual or each amount of what kind of, depending on what sort of analysis we are doing, will depend on that. Each class j has its own set of coefficients. These are the coefficients. That means each class will have their own beta coefficients for each of the parameters. Only the difference between class scores matters, not their absolute values. So again, because we are doing, that's why we are taking a reference to a base class. So that means the difference between those classes are taken in the scores, of course, and then we are not taking the absolute value, same as a binary logistic regression. So the difference actually tells us that, okay, if that z value increases, then the probability of choosing one of those classes, mostly based on the reference class, that would increase. And setting base class score to 0 makes the model identifiable and estimable. So that's why we are make that one as the the 0 value, and what is more than that is taken for the other one. Scores do not represent probabilities, how each observation belongs to a class relative to the base class. So the scores actually is not a measure of what is the probability of choosing that particular alternative. It just help us to determine which should be the choice when two alternatives are taken, which could be the choice, of course, relative to the base class. Then the probability calculation is where we convert the linear score into using the sortment function. We will convert it into a probability score. So instead of sigmoid, we use the sortment function, which is a multi-class generalization of the sigmoid function, and this probability function, this looks like this p, where for yi the outcome is j. In that case, this should be that the probability is estimated as e to the power zij divided by summation m equal to 0 to j e to the power z im, where m value is for all the classes. We add those up, and then we can find the probability of the class j. And then all probabilities lie between 0 and 1, and the probabilities across all classes sum to 1. Again, here we will also take log odds, and for any class j relative to the base class 0, the 0th class, of course, this is the log odds that we have, like earlier we have done in binary logic, and this side is the actual score. So this score is where we are converting it into, that means this is the linear form, right? So that means because we are taking log, we get the linear score on this side. So MNL regression is linear in the log odds and not in the probabilities. That's why we are taking it. It's in the taking the log odds in for this, because then it becomes easier to determine the beta scores. If xk increases by, what it says is, we already have learned this earlier, that is, if xk increases by 1 unit, any one of these, it increases by 1 units, then the log odds of being in class j instead of base class changes by beta j k, right? So that means the probability increases of that to be in class J, and that is positive BJK, say it means class J becomes more likely than the base class. Negative BJK means class J becomes less likely than the base class. So it all depends on the sign that we are choosing. Then comes the odds ratio, same way we have done earlier. Odds ratio is basically new odds divided by old odds, that is e to the power bjk. Now it tells us that how the odds of belonging to class J relative to the base class, of course, change when a predictor increases by 1 unit holding other variables constant. That is, when the predictor, that means xk or anything, changes by 1 unit, what is the odds of belonging to a class J and how, how likely it is, and that would be estimated. So e bjk, e to the power bjk is greater than 1, that means odds increase and class J becomes more likely relative to the base class. If it is equal to 1, then it indicates predictor has no effect, and then of course bjk is the predictor strength, the importance of that predictor, right? So e bjk is lesser than 1, that means odds decrease and the class J becomes less relative to the base class. So taking an example, if the base class is walk and class J is the metro out of many other classes, then and the predictor is distance to metro station like earlier, what we can say is beta of metro for this particular distance, this particular predictor, and we get a value of minus 0.5. That means it's a negative, as we have known that if e to the power minus 0.5, the value is 0.61. For each kilometer from a metro station, the odds of choosing metro rather than walk, because that's the reference class, decreases by 39%. So holding all other variables constant. So this is decreases by 39%, that is 1 minus 0.61. So it is decreases, right? So or it could be increases in that way as well. So we can then, in that case, we will take 0.61. So because we are saying that for each kilometer from the metro station, the odds of choosing metro rather than walking decreases by 39%, and considering everything else is constant. The model, then of course, once we have that, we can estimate the model parameters using the maximum likelihood estimation here as well. So again, we maximize the likelihood of the observed choices as per the model. Then obviously, based on the observed data set, we will run the the probabilities and all, and by changing the beta parameters, we can find out the fine tune the values of beta. The overall likelihood is the product of these probabilities across all observations. So likelihood, this is the likelihood function. So we are taking the product of the probabilities of all the different observations, that is Pij to the power Yij. So this again we take a log likelihood of that. So we take then it becomes this summation Yij into log of Pij. So this, because I have taken log of likelihood, so this log value, this Yij value is the determining factor. If Yij equal to 1, then if it is 0, accordingly we will record that value or not, and then you can say if y is equal to 1, if the observation I belongs to class J and 0 other, it will belong to class J and 0 otherwise. The model estimates beta by maximizing this log likelihood function. So again, I'm not getting into details of how to maximize and all these things, because for that we have to get into we will have to look into the more detailed statistics of it. But what it means is this is the formulation where we will put the we will take Pij value, as we have already learned the probability earlier. So we will multiply with the this Yij, and then based on the actual observations we will add these values up, and whichever values maximizes for values of beta, that we will adopt. So now coming to the model, in this case what we are doing is we are trying to understand the location choice behavior of households, otherwise known as the residential location choice model. We have done a revealed preference survey in nearby to Kolkata in the Bidhannagar Municipal Corporation and the New Town area. So this is a satellite townships of Kolkata. So what we have done is we have gone to a house and we have ask the decision maker of the house. That's an assumption that the decision makers, whatever he says is the correct choice. Based on his decision, the movement, the location would be chosen in future. And then this location was chosen, and 4 broad location choices were considered, and this is a revealed preference survey. That means already people have moved there. We have asked them that have they moved there recently or not. If they moved there recently, that means they have moved there and moved to this particular location. And then we are trying to find out which, depending on who has moved where, accordingly we can determine that what is the probability of choosing a particular location from that. So what we have done is we have asked them questions about their religion, their monthly income, the number of members, the age of the household head, the gender, the marital status, education, occupation, family type, total children, number of workers, and then origin of the household, is it local or migrant, how many car ownership has got. So these are the different variables that we have used. And you can see that some of them are numerical, some of them are categorical, and we are trying to find out, based on these characteristics, which are the likely location a person would choose. And that we have used a revealed preference survey to determine that. So in addition to that, these variables were all the socioeconomic characteristics. In addition to that, we looked into the housing characteristics, what type of housing they are looking for, then plots or what type of housing they have moved into, the plot size, the ownership, the median rent, the median cost of that particular area, and then the residential. Then what we have done is, of course, the location characteristics of that particular location, how far away it is from their what is the walk travel time, how close it is to public transport, what is the travel time to school, the density of that area, the percentage of commercial land use, which we felt that also influence our location choice. So location choice is influenced both by location characteristics, housing characteristics, as well as socioeconomic characteristics. Based on all this, a person decides. Based on these characteristics, people actually choose a particular area. So we have already taken people who have chosen an area, and then we have estimated why they have chosen an area, right? And so these location choices are 4. So we have divided the entire zone into 4 broad zones, which were more or less similar. And you can see this location 1 is A, location A is 1, location B is 2, and this is how the coding has been done. And the variable name is location underscore 4 choices. Whereas you can see that, okay, the variables that has been adopted in our program, these are the variables for each of this particular, these characteristics or attributes that we have taken. Are they numeric, are they categorical, everything is also listed as well. So this is the data file, and then you can see these are the columns which are listed one after another. This is the CSV file, and these are the actual values for each of that. The end, this one 1 1, this actually tells us the final choice. So now coming to the model in Python, we will import pandas, numpy, sklearn, different parts of it as we have done earlier, that is import train test split. We are importing the one hot encoder as well as the standard scalar for converting the variables. For that we have column transformers as well. Then there is a pipeline, and then we are importing the logistic regression model, and from we are also importing the different matrices such as confusion matrix, classification report, accuracy score. And once we have done that, then what we do is we load the data set. Residential underscore location is the name of the file in D drive which we have loaded, and then we are of course printing it to see its shape as well as the column names that are available. So df.column to list also actually lists the column names. So you can see this is the shape of the data. There are 210 rows, and then there is 26 attributes or features. And the column names available in the data set, these are also listed one after another, and this would be matching. These are the column names adopted in Python. So the target column is location underscore 4 choices. So this is the target variable, this we have to predict. and these are the different attributes. Feature underscore columns equal to religion, monthly income. These are the columns from the data frame that we are taking for, which we are loading as features. And then once we have done that, this is the list. What we can do is we can do a very quick check. Again, these are not required, but if you are not sure that if there is something missing, that means whatever columns that you are, that means this list is called missing is created. A list called missing is created. It checks all required columns, that is the target variable, target column, and all predicted variables, the feature columns. If any of these columns are not present in the dataset, they are added to missing. So that is, if somebody wrongly puts something, then it can check. If the missing list is non-empty, the program stops immediately and an error message is printed showing the columns which are missing and suggestions for spell check or some spelling check or some error has happened, right? So this is just a, a precaution that we are doing. There is no point of putting it if you are absolutely sure about all this, but sometimes we can keep this in the program, in larger programs and all, so that suppose this has to be entered by somebody, then some mistake happens, this could be taken care of. Then we are keeping only the required columns here, so that is both the feature columns as well as the target column, and we are putting it in data. And then so first we are taking we are dropping the subset target column from over here, and X data equal to the feature columns and Y data is the target column. So this first we are dropping target column, and whatever is there, that is becomes the feature column, and then this Y becomes the target column, of course. So then we are creating a label map with 4 locations listed. This is just again optional. We can add this so that when the program lists all this, we always list as location A, location B instead of the values like 1, 2, 3, 4. And that's once that is done, we determine which are the categorical and the numerical features. So first we separate them. First we list the categorical features over here in this list, and then after that we list the numeric features. And once we have done that, again we can run a check, same as earlier. That means we check if any feature was not categorized. That means we take the total number of features minus categorical features, numerical features. If something remains, we can again raise an error saying that something has been, some is missing. So once it is done that, raise value error, these features were not assigned to categorical numeric. So we can list those features which are not assigned, but here we have taken all. And then we do the pre-processing. That means we call column transformer, and then we can run the one hot encoder and the standard scaler to convert the numeric to scale values, numeric variables to, we can scale the numeric variables as well as we can convert the categorical variables to dummy variables. So this is what has been done, and we are dropping any column not explicitly listed using this this remainder equal to drop. So once we have done that, then of course we will, this is the X train, X test, Y train, Y test. This is where we are doing the split, and we are also again using stratify Y equal to name. This helps in keeping the class proportion same as in binary logistic as well. The test size is 0.3, which means 30% is reserved for testing. Random state is 42. So once we have done that, then once the split is done, then we are calling the logistic regression model, and then we are within that we are also specifying that total iterations would be 2000 times, and the solver would be LBFGS, and the function would be softmax, right? So and of course in multinomial the regression the function that is used is softmax function. So once it is done, then we create the pipeline, which is the pre-processing step, as well as the model, calling the model MNL, which is over here. And once we have done that, what we can do is, once this pipeline is ready, as earlier, we can now train the model like pipe.fit. We push X train and Y train into the pipeline, so that now accordingly it will take the data, and we already have specified what is X train and what is this Y train, and then this would be, then similarly we push it into pipe.fit, and then y.pred actually predicts the probability or rather it predicts for X test what is the value, and once we do that, then we can also predict the accuracy score by taking Y test and Y pred, and then we can print the results where we get accuracy, confusion matrix, and then classification report, and so on. So over here you can see that the accuracy value has come as around 0.873. Then this is the confusion matrix. There are 4 rows given because we have 4 outputs. So there are 4 actuals, and the rows are giving you the actual values and the columns are giving you the predicted values, and accordingly we can say which is correctly predicted or not, or which is predicting what. And then the classification report actually tells us that for each of the locations A, B, C, D, and what is the precision value, what is the recall value, what is the F1 score and the support, and accordingly we can also find the accuracy values, macro average and weighted average. And once we have done that, then we can predict the probability using our trained model. We can predict the probabilities of the 5 test cases. So that is where when we say pipe.predict underscore probability underscore proba X test, it will predict the probability of the 5 cases. Now once we do that, then what is done is the model outputs the probabilities of each of the classes. That is that means whatever is being predicted, and what we do is we choose the one which has got the highest probability as the class which is the assigned class or the predicted class of that particular that for that particular observation. So that means it will predict for all the different classes, but we will choose the one which is the final result would be the one which has got the highest probability. So I will show that in results. And so once we do that, then this pd.dataframe, this proba, this one is this probability values, and what we are doing is the column names are also taken. That is the class names from we are taking that, and then we can say that for each column what is the probability value, and then we can print the first test observation, and we can print the first 5 both the predicted as well as the test values, and we can print. That means we go to the actual class values is already listed in y underscore test earlier, and then we can predict the 5 locations, 5 predictions for that for the first 5 values, and also we are predicting it for the first 5 values and to show that what kind of results are we getting. So that means is it matching with the actual results or not. So I will just go to the results and I will show that first. So first we are predicting the probabilities of 5 test observations. So you can see location A, location B, location C, location D. For each one the probabilities are predicted, but I will choose the one which shows the highest probability. So for the first case, that is the 0th case, obviously this is showing the highest probability, location D. So the predicted class is location D. So that is chosen. For the second case, the predicted class is location C. This is location C. For the second one, the predicted class is this one, location D, and so on. So you can see now when I am printing the actual classes of those same observation from Y test, that you can see that these are also being predicted, which is exactly the same that we are predicting. So that means our prediction is matching with actual. So that is what is happening over here. So this is the actual class and this is the predicted class. First we have to store it, of course, and then we are showing that. And then what we are doing is we are then determining the coefficients and the odds ratio. So for using this pipe.named underscore step, so we are using the first getting the categories that we have used, and then for each of these categorical features we are and the numeric features, what we are doing is we are determining the coefficients that we are getting, and this coefficient and as well as the intercept. Once we are doing that, we are storing it in a data frame, and then we are going to print it. So class names, columns, or first of all features and all is being given along with the coefficient, and then we are printing coefficients along with log odds as scale, and we can predict it like this is being printed, and then we will see the results, of course. and then when I do the coefficients I log till 10, that means it prints first 10 columns to keep the output readable, and then I print only the first 10 coefficient column, and that's I just that I can print it out. And once we have done that, we can also estimate the odds ratio by taking the np.exp. So np is what, so we are taking for each of the coefficient we are taking exponential, and then we are printing the odds ratio as well for the first 10 columns, and once we have done that, we are printing the intercepts of the class, and then finally along with the class names, of course. So over here you can see that the log odds has been printed. So this side are the different categories, location A, B, C, D, and you can see for each. So this is the for each of the coefficient, each of the predictors, that is the xik values, we are getting the beta values over here. And then what we have done is we have also printed the intercept as well for each of these classes, location A, B, C, D, because beta 0, these are the beta 0 values, and these are the beta 1, beta 2, beta 3, and so on, those values. And these are the odds ratios. This is the exponential of the beta values, right? These are the ones we have taken e to the power of the same value. Now, what is happening over here is what we have learned in multinomial is that we should always predict based on the probabilities, particularly over here, based on relative to another class, right? So, although multinomial logistic regression requires a reference for identification, because we are using sklearn, we use a symmetric softmax formulation so that coefficients and odd ratios are estimated and shown for all locations, and interpretation is always relative across locations. So that means for example, holding everything constant, income 2, that is one of the, that's not shown over here, but it's there as well, that is not printed. Income 2 is, which is one of the, predictors, increases the odds of choosing location B relative to other locations. So this is how we should interpret the results, right? So that means we show them that how each of these parameters are important, how it is playing a role in that. So that is where using these results, we can compare between the odds of getting chosen, which location to get chosen, and which parameters influence which choice, right? So the models predict the probability of choosing one location A, B, C, D, and one category per categorical variable is the reference category. And that means whenever we have used the categorical variables, what we have done is we have not taken all the categorical variables. Of course, one is variable is dropped, so that becomes a reference for that variable. So if there is male and female, we drop female. So that is whatever is predicted is for male. So obviously the other is female. So whatever is, the opposite is true for the female. And that means if the coefficient indicates that it increases for male, that means of course it decreases for female. If there are 3 variables, categorical variables, in that case what happens, we have 3 dummy variables instead of I drop one of them. So that means it is always in reference to the other dummy variables I am predicting. And this is actually made sure when we are running the model. And earlier, so where you can see that when we are using the one-hot encoder, we have used drop equal to first. So when all dummy variables are included, interpretation by comparing coefficients across categories, dropping one category creates a clear reference group and simplifies interpretation. So that is what we have also done over here. So the model predicts the probability of choosing one location, and one category per categorical variable is the reference category. Model output log odds, coefficients, beta coefficient, as well as the odds ratio exponential of beta. We interpret the odds ratio, of course, and when odds ratio is greater than 1, it increases likelihood of choosing location. If odds ratio is equal to 1, there is no effect, and odds ratio is lesser than 1, it decreases the likelihood, obviously considering all other variables as constant. So these are the references. And to conclude, multinomial logistic regression offers a systematic way to explain and predict urban choices by linking individual, spatial, and contextual factors to relative decision probabilities across multiple alternatives. Thank you.